we are going to discuss implicit differentiation. And you're probably thinking, we already did derivatives. That was chapter 12. Well, we did, but we didn't do one particular kind of derivatives, and it's not one that comes up a lot, but it is one that we do need to go into. And I do guarantee you there will be, not just on the next test, but there will be a question on the final exam that you will have to do implicit differentiation. I am not a mean person. I will not find the most complicated one I can and make you do that. But the process is relatively simple. It only gets ugly when the function you're trying to take the derivative of is ugly. Okay, so we're going to try to stick to some that the math's not, the algebra is not going to be too hard. I like a man that bargains. I don't think you, but then that's, well, I was going to say that might work if you are pretty good at doing implicit differentiation and you don't make any mistakes. But for the rest, no. Okay. All of the functions that we have been dealing with up to this point are where we have y is equal to some function of x. Okay? Y is on one side of the equation, and the part where the x is in it's all on the other side. That is called an explicit function. Okay? When y is on one side all by itself and all the terms that have the x's and stuff in it's on the other side, that's an explicit function. These are all explicit functions. The derivatives of those are all easy derivatives to take. However, we have an equation 4xy minus 3x is equal to 6 could be solved as an explicit function of x if we just do a little algebra juggling. What we would do is we would take that original function, we would add 3x to both sides, and then we would divide both sides by 4, and we would have an explicit function. This function, before we do that, is called an implicit function, meaning that the x's and y's are all mixed up together. And that will present us with a problem. So if we had to actually take the derivative of this particular implicit function, we could do it easily by turning the function into an explicit function and then apply your quotient rule. Okay? So certainly we feel like at that point, well, we know how to do this. But here's the problem. Some equations in x and y can't be readily solved for y. And some of them can't be solved for y at all. You can't do it. It won't work. Some examples of those, it wouldn't be that hard to solve this equation for y because you could use the quadratic formula. It'd be a little ugly, but we could do it, okay? But you can't take this problem and solve it for y, because that's not a quadratic equation, therefore it's not going to be applicable to the quadratic function. If it's factored, you might be able to fiddle around with it, but you're looking at that equation thinking, I don't want to factor that. That's nasty, okay? That would be terrible. So in those two equations, y is said to be implicitly given in terms of x. So it's still a function, but the x's and y's are mixed up in the terms. And because of that, we're going to have to learn to find the derivative, which we've been calling dy dx or y prime. We're going to have to do it by a method called implicit differentiation. And what we're going to do is we're going to assume that there does exist some function or functions that you might not be able to find y equals f of x, but the derivative will exist. So what we're going to do is we're going to have to be thinking about the dy dx here, and in order to find f prime of x, we're going to have to do a little algebraic magic. The main thing to keep in mind is if you have a function, the function is y is equal to f of x, x is the independent variable, and y is the dependent variable, and the value of y depends on x. Okay? Y is the dependent variable. That's going to make a difference when we do this problem. So here's our first example. We cannot readily solve that equation for y. We could juggle it around to where we might be able to turn it into a quadratic formula problem, but it would still take longer to do the quadratic formula to come up with the explicit function and then have to take the derivative anyway than it would to learn how to do this implicitly. Okay? So this is the way this works. We're going to take the derivative with respect to x on both sides of the equation. Now, the derivative on one side of that equation, piece of cake. Right-hand side, what's the derivative of 10? 0. No problem. Other side, we have a few rules we could follow. On the other side, what we actually have is the combination of two terms that are being added together, so we could take the derivative of each term separately. But if you take the derivative of 3xy with respect to x, x being the independent variable, what we actually have here is that y is a function of x, and that is a product rule problem. Okay? What you want to do in every one of these is you want to separate out the idea that y is an f of x. And if y is an f of x, that's 3x times an f of x. Okay? So in order to take that first derivative, we're going to look at the derivative of 3x is 3. And the derivative of y is dy over dx. Or you can use the notation y prime. Okay? It won't change anything. And you'll actually see me switch back and forth and do it both ways because it works both ways. So my first step for this derivative is to do that product rule. So the product rule says first factor times the derivative of the second. And remember, you can write that as y prime if you want to. Plus the second factor, the second part, times the derivative of the first, which is 3. So we have differentiated now the first term. It doesn't look like what you're used to seeing, but that's okay. We're going to keep going. Now we take the derivative of the second term. Keep in mind that y is a function in x, and that function has been squared, which makes it a chain rule problem. Y's raised to a power becomes a chain rule problem. Okay? So that means its derivative is going to be 2 times 4 and then that'll be y to the first times the derivative of the inside function, and the derivative of the inside function is 4y, or in other words, dy dx. Okay? And that dy dx is going to be multiplied by 2 . So what we're going to actually come out with, whoops, no, not there. I'm sorry, I wrote that down and didn't mean to. So what we have is 4 times 2y to the first power, that's not a prime, that's to the first power, times dy dx, which is the same as y prime. And the derivative over here was 0, so that whole thing is equal to 0. So step 1 is you take the derivative of every term. So you have to remember that y is a function in x, and that means you might need to use the product rule, the quotient rule, or the chain rule if y has been raised to a power. Okay.
The last part of that, you had 2
Y prime or dy over dx. That's chain rule. That's chain rule because you brought your power down in front, get what was inside the parentheses, but you reduced the power by 1. Okay? But then you need the derivative of what was inside the parentheses, and that's dy over dx. Okay? Because it was y that was being squared, so we just need its derivative. Okay? So actually, I think this looks better if I write it the alternative way. This is one way to write it, but it does actually kind of look better if you write it the way that I normally think of doing it, because these tend to bother people. Okay? So let me rewrite this, calling this 3x y prime plus 3y plus 2 times 4 is 8y prime is equal to 0. Now those two say exactly the same thing. It's just you don't have that dy dx kind of messing with your mind. Okay?
So you don't take the derivative of y. You
just say, well, see, you don't know what the function is that y is representing. You just know that it's a function in x, but you don't know what the expression is for it. So we're just saying, okay, it's a function of x, we're going to take its derivative. Every time you see a y, you have to take the derivative of y. Just call it y prime and write it down and keep on going. Okay? If y is raised to a power, then you might have a term of y left in front of that. Like y squared, the derivative is going to be 2y prime. Okay? Do all of those terms have a y prime in them? Which one doesn't? Okay. Let's move him to the other side. Okay? Now, it's not immediately obvious to you why you wanted to do that, but that will be your next step. Find all the terms that don't have y prime in them and move them over. Yes, it would. Thank you. That will be a negative 3y. So where we are right now, and I'm just going to recopy the step to make it kind of more obvious where we're going with this. That's where we are right now. And this is what I want you to notice. There's a y prime here. There's a y prime there. Both terms have a y prime. Factor it out. That's what we're going to do next. We're going to factor out y prime. So if I factor out y prime on that first term, what I have left is 3x plus, if I factor out y prime from this one, I have left 8y. Everybody know where I got everything? You're probably not clear yet on why I did it, but in about 30 seconds it's going to be clear to you why I did it. What are we trying to find? What are we trying to find? The derivative dy dx. We're trying to find y prime. Look what happens if I divide both sides by what's not got y prime in it. There's your expression for y prime. There's your derivative. Okay? You have all the other rules you learned back in Chapter 12. Those are still in existence. They work fine. If you're ever taking the derivative of y, its derivative is y prime. So if you have a problem where, there's a y prime, a y mixed up with x's, that's going to be a product rule. Or it might be the x part over a y part. That might be a quotient rule. Or if y is raised to a power or under a radical, that's going to be a chain rule. So you go ahead and do whatever the appropriate thing is to y, but then you tack on to the end of it y prime. Okay? There's always going to be a y prime because the derivative of y is y prime. And then at the end, you get all the non-y prime terms on one side and the ones that have y prime on the other side, so you can factor out y prime and then get it by itself. This should take you back to your algebra days when they gave you the equations that had nothing but letters and said solve for one of the letters. Remember those? This is the same thing. That's what they were trying to get you ready for. Unfortunately, it's a long time usually between then and now. Okay? So here's your set of steps. If you have an equation where the terms have x's and y's mixed up together, you differentiate both sides of the equation with respect to x, and keep in mind that y is assumed to be a function of x. It's an f of x. Meaning that y prime, or dy over dx, is equal to the derivative of y. And you can use either notation you want to. You can use the dy dx. You can use y prime. I like y prime because I think it's just less confusing. Then you use algebra, and you put all the dy dx terms or the y prime terms on one side, and then all the other terms that don't have dy dx on the other side. Then you factor out your y prime and solve for y prime by itself. So there's your steps. And the only way to get good at it is to practice. Yeah, I told you I was going to do some ugly ones for examples, because if you follow the ugly ones, then the non-ugly ones are a piece of cake. Okay. Okay. This is an equation. We cannot separate out the y's from the x's because it would be too complicated. However, we can take derivatives of every single term. The first thing I want to do, though, before I try to do that, is I would like not to have radicals, because I don't have a radical rule for taking derivatives. I only have the power rule. So I'm gonna rewrite the function as x plus x to the 1/2 power times y to the 1/2 power is equal to y squared. And now I have things that are all power rule problems. Make notice of the fact this is a product. That is a product. The derivative of x squared is 1/2 x to the negative 1/2. But the derivative of y squared is also 1/2 y to the negative 1/2 y prime. Every term that has a y in it, when you take its derivative, you also have to add on y prime, because that's the derivative of y. So my product rule part here is going to be x to the 1/2 times 1/2 y to the negative 1/2 y prime. There's the product rule part. Then we got what I like to call the easy part. What is the derivative of just plain old x? 1. Then we've got an equal sign, and we need the derivative of y squared. That's going to be chain rule. because there's a power. So you bring the 2 down in front, times the y, and then 2 minus 1 is 1. And then the derivative of y is y prime. Now make sure you know where everything came from. Where the x to the... Okay, it's this, and it was being multiplied by the derivative of that. Oh, and wait, I just realized I left out a term. Yeah. Yeah, I was so excited to be getting done, I forgot, I left out a step. So I also need to do, and since it's going to be a product rule, it'll be plus, I need to take y prime times x, 1/2 x to the negative 1/2. So I actually now have 3 terms on the left-hand side because I get 2 terms out of the product rule. Oh, and I left out a y prime here. Okay? Now that looks pretty ugly. I'll give you that. That looks pretty ugly because of all those fractions and the negative and positive exponents. So I know that looks ugly. It might not look quite as bad if we could figure out a way to clean it up a little bit. These 1/2s are killing me. I'm going to multiply that whole side of the equation by 2, which means I'm also going to have to multiply the whole equation, the other side as well, by 2. But I can get rid of the halves that way. So if I multiply 2 times 1, I get 2. And 2 times 1/2 will turn into 1, which means then I have x to the 1/2 power. And since that y to the 1/2 power is negative, it doesn't matter. I'll just bring it on down and write y to the negative 1/2 power. And then I got a y prime. And remember, that's a prime. That's not an exponent. That's a derivative. And then 2 times this 1/2 makes that 1/2 go away. And what I have left is y to the 1/2 x to the negative 1/2. And since the derivative of y is not over here, there is no y prime. No. No, because the 2 is multiplying times the 1/2, but you've not changed the powers. You can't.
I don't talk about, like, shouldn't that, like, in the second term where y is the 1/2 and parentheses 1/2, there's not a 1 in front of the y that you're multiplying 2 by multiplying 2?
Yeah, but you already multiplied it because it's 1/2, y to the 1/2, x to the negative 1/2.
So when you multiply 2 by that x to 1/2, it's just
Yeah, it just makes it disappear.
what did disappear?
Hmm?
There's x to the 1/2 right there, we're multiply that second term.
Those are powers, though. What I made disappear was the coefficient that came in front from the power rule.
Yeah.
Okay?
Maybe that would be multiplying. I mean, maybe I'm overthinking it.
Okay,
I would read that into a computer. If you're multiplying everything by 2, I would assume it'd be
Okay, let's go through one term at a time. Let me rewrite the equation first. No, that's okay. If you don't understand, then I want to make sure that you understand why we're doing what we're doing. So in order to make this easier to deal with, I'm going to take this whole term and put the 1/2 out in front. I'm going to multiply everything out. Okay? And then same thing here. I'm going to pull that 1/2 out in front because it's actually being multiplied in with y to the 1/2 and x to the negative 1/2. Okay? So now here I'm going to go and I'm going to multiply everything by 2 all the way across. So 2 times 1/2 disappears. 2 times 1/2 disappears. 2 times 1 is 2. This has disappeared, and all I have left is what was in the parentheses.
So in the original one, you just flipped the 1/2, the coefficient 1/2, and like the x to the 1/2 and y to the 1/2. You just flipped those.
Right, I just flipped them around so that, because remember, you're multiplying, and the order of the things you're multiplying together doesn't matter. Okay? And the only reason I'm doing this, you could actually do it without what I'm showing you to do. The only reason I'm doing this is because that 1/2 tends to get you distracted when you're trying to do the rest of the problem. So one of the things I like to do is clear the fractions if I can. So then, since this is gone, I now have just what was left in the parentheses. And then 2 times 2 is 4y prime. So for that equation, do you see where everything has come from now? Now we could simplify it even further. We could go back to the radical notation, and we could take the negative exponents to the denominator. We could do all kinds of things, but it isn't going to make any difference in the end. It's just another extra step that we can avoid as long as you're okay with doing it the way it is. Remember, your next step is find the terms that have the y primes in them and get them all together. Well, I got a y prime over here and a y prime term over here. And I would like for them to be together on one side. So I'm going to move that term, x to the 1/2, y to the negative 1/2 y prime, over to the other side. Which means I don't have it over here anymore. All I did was move it. So here's what I've got left. The 2 plus y to the 1/2 times x to the negative 1/2 equals 4y prime minus x to the 1/2 y to the negative 1/2 y prime. And what I want to do is I want to factor out the y prime, because that's what I'm trying to solve for. So now I've got an equation where there's no y primes over here. I factored out y prime over here, and I can get it by itself. So I have an expression for y prime. It is not a pretty expression. When you do implicit differentiation, there's usually not any beauty contest involved. No, because remember that's being added to 2 and subtracted before y. You can't cancel term to term. You can only cancel out things that have common factors. Okay? I don't know what you're doing or why you're there, but go away. So remember, anytime you've got that and that going on between, there cannot be any cancellation. Okay? Just leave it right where it's at. You can't clean that up any further unless you want to go back to radicals. Okay? Now, if you can get through that one, you probably could do just about any of them. Because that's about, I mean, there's uglier ones than that, but not a whole lot uglier. So we will go to an application problem. And the application problem is our last example for the night. We have a demand function. And the demand for this commodity that we're looking at is given by P, where P is the price in dollars and Q is the demand, in hundreds of units. And what they tell us they want us to find is find the rate of change which is the derivative, which also can be indicated by finding the marginal demand with respect to price when Q is equal to 100. So the value of Q is going to be 100. It's going to be a numerical derivative. The only thing is, because this is implicit, you're not necessarily going to be able, actually it's not, well, wait, demand with respect to price. Actually, that's not even an implicit problem, I don't think. Yeah, it's 500,000.
No, on the bottom. Well, no, on the bottom, like the comma is
Yeah. Okay, now here's why we have to do implicit differentiation, okay? We're going to find dq dp. P is a function of Q, okay? So we're going to take the derivative of this side, and we're going to take the derivative of this side. Okay? And we're going to take both of those with respect to Q. So the thing you want to remember is that the derivative of P is 1. Okay? The derivative of P is 1. Then we need the derivative of this. And you would probably be tempted to say, I could do quotient rule with that, but I wouldn't. The reason I wouldn't do it is because you don't have any Q's in the numerator. So I wouldn't do quotient rule. I would change that, and over here I'm just going to, I've already told you P is equal to 1, so we're going to remember that and put 1 equals down here. This is easier to see if we have P is equal to 500,000 times 2Q to the third power plus 400Q plus 5,000 to the negative 1 power. Yes, yes, because that way we don't have to do quotient rule. The answer, if you did quotient rule, would come out to be the same because the derivative of your numerator is going to be 0, and it would make the other term disappear anyway. But this is still simpler in the long run. Okay? So what is the derivative of this? Okay? P prime is actually equal to negative 1 times 5,000, or 500,000, times 2Q to the third power plus 400Q plus 5,000 to the negative 2 power. That's just power rule. But because this is inside parentheses with an exponent on the outside, this is chain rule. So we need to multiply that by the derivative of this, which is 3 times 2 would be 6Q plus 1 times 400 is 400, and then Q would be to the 0, so it disappears. And then, oh, yes, thank you. And then the derivative of 5,000 would be 0, so we're done right there. Okay? So then this would be dq dp, or P prime. Okay, that's what P prime is equal to. Well, you've got to differentiate the whole equation. Because this is not solved for Q, it's solved for P. So that's why in the original part of it I said, remember, the derivative of P is going to be 1. And that's going to be equal to this. Okay, I think it's good now. And this is actually where the dq dp is over here. Because remember, this is an expression for P, so we're having to take the derivative of the Q part of this. And f of Q is what this stuff in parentheses is.
So what rule are we using again right there? The general?
Yes.
So the derivative of the whole thing, or times the derivative of the side? Okay.
And then times dq over dp, or you can call it q prime if you want to. No, q prime. Q prime. Remember, up here, P is a function in Q, so we're treating the Q as actually the independent variable, which means P is the dependent variable.
The whole thing right there is P prime times Q prime.
Yes. Now that we've got all of that big long mess, the only thing we have left to do is substitute in Q equals 100, because that's the equation. We don't need to solve for anything in particular. That's the whole equation. We can wait till the end to solve for this. Okay? That's actually what we're going to solve for. But since we're going to plug in numbers, we may as well go ahead and plug them in. So 1 doesn't change. Since this is a -2, I'm going to put it in the denominator because it'll make it easier to keep up with the separated calculations. So that's what I did with that. I'll leave my -500,000 in the numerator. And then I add this part. No, you could do it that way. That would work. But just for the sake of, seeing where I put everything, I just separated it out, but you could do that. Now, the thing to remember is that this is all equal to 1, so all of the arithmetic, once we're done, I'm going to try to give you the, because I've already worked this one out. That turns out to be -500,000 times 60,400 over 2,045,000 to the second power. And that's still all equal to 1. Because the derivative of the derivative of P is 1, because it's 1P. Okay? The derivative of P is 1, because that's what we're taking. Okay. Now what we want is dq dp. So this is equal to 1. How would we get rid of all of this and get dq dp by itself? Well, actually what we're going to do is we're going to divide both sides by that. Okay? But when I divide 1 by that, What I'm really going to do is I'm going to take that thing I'm dividing by and flip it over and multiply times 1. Okay? 1 over that looks like this. No, because I'm flipping it. I'm just flipping it. I'm not moving it. I'm flipping the whole fraction so that instead of dividing by the fraction, I'm multiplying by the fraction. Okay? And again, you don't necessarily have to do it like I did. You could have kept this. But the reason I did it the way I did was because it's easier to see that when I divide both sides by that I'm going to flip it over. Okay? So here is the numerical value of your derivative. We just have to do a little arithmetic. And it turns out that this is actually about negative 138. Flip it, multiply. Because we're saying 1 over that fraction, and we want to actually complete that, so when you have 1 divided by a fraction, then you take 1 times the reciprocal of that fraction. Okay?
You can just go ahead and solve the fraction and then divide over, like the negative 500.
Yeah, you could. You could have actually, you could have done that in this step. There's more than one way to get at this problem. Yeah, you could have gone ahead and got a number for all of this, and then done 1 over that number, 1 divided by that number. You'd still get negative 138. Okay, because it comes out to be about negative 138. So you could have done it in an earlier step than I did. Okay. Now, we've got a number. The hard part was getting the number this time. What does that number mean? When demand is 100, and remember it says up here it's in hundreds of units, so actually that's 10,000. Realistically, that's what hundreds is 10,000. Demand is decreasing. By about 138. And either use the word dollars, or put a dollar sign in there. Per $1 change in price. Because remember, that's actually what we were finding was as the price changes. Because it was the derivative with respect. It was the derivative of P with respect to Q. So it's per $1 change in the price. So basically what we're saying here is that if you make 10,000, if the demand is 10,000, your demand is decreasing by 138 for every dollar you increase the price. Oh wait, I said no. I'm sorry. That's my bad. It's not $138. It's not $138. It's actually go back up your way. In hundreds of units. So it's 138 or 13900 units. which would be 13,800 units. I put my dollars in the wrong place.
But how do we know it's $1? What is that? Does that have anything to do with something derivative of P?
Yeah, that's because it's a derivative of P, so if the price is changing, and if you change the price by $1, that changes the demand by hundreds of units. Okay? So does anybody have any questions? Now, I will tell you what I am more likely to do on a problem like this, because it's in class, because it's an in-class test. What I'm more likely to do is give you that problem set up and then say, given that the derivative with respect to Q is, and then tell you what the derivative is, so that all you have to do is plug in and explain what it means. I don't know that I would want you to differentiate that complicated a function. Well, I mean, if you don't need to. Because for me, the applications problems are more about interpreting what the answer is. So I can tell you the how much part, and you just explain to me what that means. Okay? Okay, if you have questions on the homework, the Show Me homework, the My Math Lab homework, anything, I will be checking email over the weekend. I am not going to post the practice test this time. I'm going to tell you that your, no, wait. I'm going to tell you that your study guide is your Chapter 12 test, and your Show Me homework. Your Show Me homework for both these sections, for all of these sections. So the stuff that you put in Show Me, that will be your study guide. Practice those. The other practice you should do is practice the Chapter 13 and 14 review quiz in My Math Lab, because I probably will pull either a problem from Show Me homework or a problem from the 13, 14 review, or both. Okay?
You said it's going to be shorter. What do you mean you're going to pull a problem, like one similar to this?
Yeah, maybe the same exact problem with different numbers. Okay? It won't be due, as in I won't take off for it as long as you get it in by then, but if you delay turning it in, then I'm not going to have time to actually tell you if you did it right or not.
Yeah, well, yeah,
although you do have right answers to aim at.
Yeah.
Okay? But if you don't turn it in time for me to say, hey, you're really messing this one up, and that's the one that's on the test, then you're really messed up.
Yeah.
Okay? Capital L-A-T-E, all caps. I don't think there's a penalty. I think I took the penalty off. Yeah. Actually, you shouldn't be at a penalty at this point, though, because we haven't had a test yet. Okay, don't do that test yet, then. Don't do that quiz. Let me go and take off the penalty, because the penalty should already be, it's not supposed to be due. It's not supposed to be due till like Wednesday next week.
Yeah.
I thought I changed it, but I may have not clicked save. There they are, both sets. First come, first served.